So today's notes are going to cover the connection between what we've been working on, which has been factoring, and we've been talking a lot of different methods of factoring, and we're going to connect that to the graph of what these polynomial functions look like. So what's important to start with today is that we're really only dealing with quadratic polynomials. Just like we've been factoring mostly quadratic polynomials, that's all we're going to worry about here. And then we know that quadratic polynomials fit the form ax squared plus bx plus c. And we know, of course, that a can't be 0, because if a was 0, that means it's not quadratic. There would be no x squared. So the most important thing for today is the graph of a quadratic function, no matter what the equation is always going to be a U-shaped graph. So here's some examples of U-shaped graphs, and more specifically, that U-shaped graph is called a parabola. So all of these are parabolas. So this is a parabola. And notice how I'm pronouncing that word, parabola. This is another parabola. And again, this shape is a parabola. Now, as we note in the definition here, it could be up like a U. In this case, this is like up like a cup, is what I like to call it. This one's down like a frown, but it's still a U-shaped graph. Maybe it's been flipped over. Now, with those U-shaped graphs, the first thing that we kind of see is there's a really important point, and that point is called the vertex. And all we want to distinguish the vertex as is either the highest point or the lowest point on that graph. Just depends whether it's up or down. Some people like to call it the turnaround point of that U-shaped. So for example, if I was following this graph right here, this point right here is where I was going down, and I changed, and now I'm going up, so I turned around. So this point right here would be the vertex of that graph, and it happens to be labeled as the point 0, 0. On this graph over here, the highest point is right here at 4, 1. So this is the vertex. And on the third graph over here, since this is up, the lowest point on that graph is labeled as 3.5, 2.6. That point would be the vertex of this graph. So every parabola has a vertex, and they could be really anywhere. It just depends where that graph changes from going down to up, or in some cases from going up to down. So the first important thing that you need to identify, like I said, is the vertex, and we labeled that in purple. Now, the next important thing that we're going to talk about today is the x-intercepts. And what I want you to notice right away is that we're now introducing some new vocabulary for the x-intercepts. We could call it the x-intercept, but the word root and the word 0 are all the same thing. So all these words are synonyms with each other. The roots or the zeros are just what x value makes the function equal to 0. And what we mean by equal to 0 is the y value. So we can go label them. Like, we know that this point right here is where it touches the x-axis. So we'd call that the x-intercept. Now, with our new vocabulary, we could also call that a root, and it is also called the 0. Just new words for the same thing. So if we look at the middle graph, this point right here, this is the x-intercept. So we could call it a root of the equation, or we could call it a 0 of the equation. This one happens to have 2 of them. There's another x-intercept here. This is another place where it touches the x-axis, so we could call it the x-intercept. We could call it the 0 of the function, or we could call it a root. Now, again, what we're noticing is all the y values are always 0. That's the definition of the x-intercept, and that's where the word zeros come from. This graph over here, it doesn't have any x-intercepts, because it never touches this x-axis down here. So it doesn't have any x-intercepts, which we could say in other words as no zeros, or we could also call it no roots. So what's important is to make sure that you memorize these definitions. So if you need to take a moment to pause and copy down the definitions. And as we saw with these examples, this function had 1 x-intercept. This function had 2 x-intercepts. This function had none. So there could be 0, 1, 2, 3, 4, 5, whatever number for x-intercepts or zeros, just depending on what the graph looks like. Now, the reason why we care is because we want to make a connection between the graphs of these functions that we're working with and what we've been doing with factoring and solving. So let's go ahead and solve this one as they want us to. Solve using factoring and the zero product property. So what we're noticing here right away is that our a value is equal to 1, our b value is 8, and our c value is 12. So if the a value is 1, we're thinking of the numbers that multiply to 12 and could somehow add up to 8. Now I know that if this number is positive and this number is positive, both numbers over here must be positive. So I can clearly see that the numbers 2 and 6 would multiply to 12 and add to 8. So my factorization would be x plus 2 times x plus 6, and that would equal 0. So then from here, I can use the zero product property. So after I factor, so I'll label that step as we factored it. Our next step is to solve with the zero product property, which I'm abbreviating ZPP. What that means, if two things are being multiplied together and they equal 0, one of these things must have been 0. So either x plus 2 worked out to be 0 or x plus 6, in which case the answers are -2 and the answers, or the other answer, excuse me, are -6. So we can see that this equation has two solutions. What we want us to then do down here is they want us to compare this to how we'd solve it graphically. So we want to think about the same equation on a graph. So we know that any quadratic polynomial is going to be a parabola. So I want to know at what x values would this parabola have the y value of 0. So we're going to go look at the graph, and you don't have to know how to make this already. You can go ahead and just copy my version down. But what we're going to go do here is we're going to make a graph using Desmos, and feel free to go get this app. It's free and it's wonderful. We're going to type in x squared plus 8x plus 12. And we're just going to look to see where this graph has a y value of 0. So on my graph here, I can see that the y value of 0 would be there, and it would be there. So on your notes, what you can do is you can just draw this function. So we have a coordinate plane here, and then it's like a U-shaped graph, and we notice it's always to the left of the y-axis. And the points where it equals 0, the first point we can see was -6, 0, and the second point we can see was -2, 0. Well, why do we care? What we notice are the x-intercepts of this function, which we can also call the zeros or the roots, right? They all mean the same thing. The important thing that we see, those x-intercepts are the solutions to our equation when it was equal to 0. And this would be important to get in your notes. So we can see here again is that when we just solved the equation randomly, when we just said, when is this function equal to 0, and we used factoring in the zero product property, we got the answer of -2, and we got this other answer of -6. And when we looked at a graph of those, what we realized is one of the x-intercepts was -2, and the other x-intercept was -6. So the most important thing for today is that the x-intercepts are the solutions to our equation when it's equal to 0. And then instead of calling it x-intercepts, we could call it the word zeros, or we might use the word roots. So below that, we can just see two quick examples of how we might ask you to use this knowledge. So question number 1 is asking us to find the roots of the equation. So what we know, and again, you can just copy this with me, is if we go look at a graph of this, so I'll get that back to back. If we look at a graph of this function, so again, I'm going to just type in x squared, so y equals x squared plus x minus 20. We want to know what are the roots. Now just remember that the word roots is just a synonym for the x-intercepts. And we know that the x-intercepts have a y value of 0. So step number 1 is set y equal to 0. So 0 should equal x squared plus x minus 20. So once we have it equal to 0, and again, we're only doing that because they asked for the roots, and by definition, the roots are the x-intercepts, where y is equal to 0. We set it equal to 0, and now from here, we know how to solve these. We're going to factor, and we're going to use the zero product property. So I do note that my a value is 1, so I'm thinking of the numbers that would multiply to 20 and somehow add to combine, multiply to -20 and combine to be a positive 1. So I know that the bigger number should always be positive, and I can clearly see that that would be the numbers -4 and 5. So my factorization would be x minus 4. I forgot a 0 over here, sorry. X minus 4 and x plus 5. Now that's equal to 0, so one of these things has to be 0, so x minus 4 could be 0, or this other thing, x plus 5, could be 0, in which case we get the answers of x equals 4 or x equals -5. So by definition, the roots are at x equals 4 and x equals -5. So what that means, if we go back over to our graph on the right side of the screen here, if I find those x-intercepts, that one right there is -5, 0. So we're correct there. And I can click the other one and see that that's 4, 0. So we're correct. One more example for us to see, find the roots of this equation. So again, whenever we see the word roots, we instantly know that that roots is the same thing as the word zeros, which is the same thing as the word x-intercept. And I think zeros and x-intercepts are a lot more easy to use to see that y must be 0. So to answer the question of finding the roots, I need to first set y equal to 0. So 0 equals 3x squared minus 17x minus 6. And then from there, I can solve this. I just need to solve by factoring and using the zero product property. Now, I like this example, and I put it on the notes here, because we notice that a is no longer 1, so we can't simply ask ourselves what numbers multiply to -6 and add to -17, because they simply don't exist. So it's a good reminder of telling ourselves that we have to list the factors of a, and then we have to list the factors of c. Excuse me, I wrote that incorrectly. That's a c, not a b. We have to list those factors. So it's either 1 and 6 or 2 and 3, and I'll worry about the signs later. So we know we're just going to kind of do some guessing and checking. So x and x, and it's nice for me that the only way to get 3x squared is a 1 and a 3. So now I got to find this combination of my outers and my inners so that they could somehow be -17. And my hint to you right now, so I just don't give it away for you, is using 1 and 3. Which one of these pairs over here would you use to somehow make an 18 and a 1? So at this point, I'd ask you to pause the video so you can figure out your factorization. And now that you've come back with your own factorization, what I would see is that if I can get the 3 to multiply by the 6, that'd give me an 18. And then the 1 would multiply by the 1 to be another 1. So if I made this negative, that would combine to -17. So the -6 must go there because I always keep my factors of a positive, which means this must have been a 1. So this was our factorization, and it's still equal to 0. So one of those things must have been 0. Either x minus 6 was equal to 0, or 3x plus 1 was equal to 0. And here, don't move too quickly. We can see that x is equal to 6, but this equation is actually going to take 2 steps to undo. I have to subtract 1, and then finally divide by 3. So I get 2 answers. Where are the zeros or the roots? They occur at x equals 6 and x equals -1/3, which as a decimal we should know to be -0.33333. So if we just go check to verify our work here on a graph, which again, you could use a graphing calculator to do. When is y equals 3x squared minus 17x minus 6? When is that going to equal 0? Whoops. So on the graph here, I can see that it equals 0 at 1/3, so that answer is correct. And then if I scroll over to find the other x-intercept, it is the number 6. So we have found them both.